Lecture 23, the Mohr circle for strain. Let's look first at the Mohr circle for infinitesimal strain. Suppose the axes of the coordinate system are principal axes, and the strain tensor, epsilon, looks like this: epsilon1, or the long axis of the strain ellipsoid, is parallel to x1, epsilon2, or the intermediate axis of the strain ellipsoid, is parallel to x2, and epsilon3, or the short axis of the strain ellipsoid, is parallel to x3. Suppose we want to transform the strain tensor to a new coordinate system by rotating anticlockwise, around x2, x1 and x3 an angle theta. The new axes are x'1 and x'3. The transformation matrix that describes this rotation is this. The new components of the strain tensor can be calculated as this, which in matrix format looks like this. Using trigonometric identities for double angles, we can simplify these equations like this. Now, recall that the diagonal components of the infinitesimal strain tensor are elongations, and the non-diagonal terms are half the shear strain. Therefore, we have these equations, which are the equations of a circle with center, E1 plus E3, divided by 2, and radius, E1 minus E3, divided by 2. This circle is the Mohr circle for infinitesimal strain, and it allows us to estimate the elongation and shear strain of a line making an angle theta with respect to epsilon1. Perhaps the main observation from this diagram is that the orientation of maximum shear strain is at plus or minus 45 degrees from epsilon1. Turning this observation around, for infinitesimal strain in a shear zone, the shortening and extension directions are always at 45 degrees to the shear zone boundary. This forms the basis for analyzing several structures, such as sigmoidal veins, the foliation in a shear zone, and the P and T axes of earthquakes, all of which are at 45 degrees to the shear zone. Now let's look at the Mohr circle for finite strain. Again, the axes of the coordinate system are parallel to the axes of the strain ellipsoid, and the Cauchy deformation tensor, C bar, which is the deformation tensor with respect to the final coordinates, looks like this. We want to transform the Cauchy deformation tensor to a new coordinate system by rotating anticlockwise, around x2, x1 and x3 an angle theta. The transformation matrix that describes this rotation is this. The new components of the Cauchy deformation tensor can be calculated as this, which in matrix format looks like this. Using trigonometric identities for double angles, we can simplify these equations like this. Now, recall that the diagonal components of the Cauchy deformation tensor are the inverse of the quadratic elongations, 1 over lambda, and the non-diagonal terms are the shear strain over the quadratic elongation, gamma over lambda. Using lambda prime equal to 1 over lambda, and gamma prime equal to gamma over lambda, we have these equations, which are the equations of a circle with center, lambda prime 1 plus lambda prime 3, divided by 2, and radius, lambda prime 1 minus lambda prime 3, divided by 2. This circle is the Mohr circle for finite strain, and it allows us to estimate the elongation and shear strain of a line making an angle theta with respect to the long axis of the strain ellipse, in the deformed configuration. This figure makes this more clear. The line making an angle theta with respect to the long axis of the strain ellipse is represented in the Mohr circle by a line making an angle 2 theta with respect to lambda prime 1. At the intersection of this line with the circle, we can read the lambda prime and gamma prime of the line. The Mohr circle for finite strain has an interesting property. A line traced from the origin to the circle makes an angle psi with the horizontal axis lambda prime. This angle is equal to the angular shear of the line. To understand why this is the case, we just need to look at this equation, which tell us that the tangent of psi in the figure is equal to the shear strain. Therefore psi is the angular shear. Therefore, If we trace a tangent to the Mohr circle from the origin, this is the line of maximum angular shear and shear strain, and from the point of tangency with the circle, we can read the orientation of the line, theta, with respect to the long axis of the ellipse. For plane strain, there are always two orientations in the strain ellipse, where the lines have not changed in length. These are called the lines of no finite elongation, LNFE. You can think of them as the intersection of the strain ellipse with the circle before deformation. On the Mohr circle, it is easy to find these lines. We just need to find lambda prime equal to 1, and project a vertical line from that value to the circle. From the intersection point, we can read the orientation, theta, of the line of no finite elongation. To learn more about this, please read these sections from Allmendinger et al., or our online computational geosciences resource. And answer these questions.